Now we moved on our first speaker, Professor Antonio Barbalace from the University of Edinburgh. He will, please. He will discuss operating system architecture for heterogeneous processing units and heterogeneous shared memory. Antonio, the floor is yours.
Thank you, Frank. Okay, I'm trying to. So I can show you do it. And then maximize. Okay, sorry, I'm not very familiar with this. Okay, so thank you very much, Frank and Huawei, to give me the opportunity to be here today. I was supposed to talk about operating system architecture for heterogeneous processing unit and heterogeneous memory, but then I thought operating system maybe is not the right word. We should call it system software, because just the operating system, I don't think can fully support heterogeneous processing unit and memory, but we need both operating system and also compiler. So the entire system software stack. I will give a brief overview of myself and my group before talking about the research. So I'm here at the University of Edinburgh since 2019. I'm a senior lecturer. And before I was US, and I also worked for a very interesting time at Huawei Germany in 2016, 2018. Before that, as you may understand from my accent, I'm from Italy, and I graduated there as a computer engineer. So in general, I like to say that I work on systems from real-time system to distributed system. They are very similar. They have CPU, memory, and storage, but just the scale that is different. And today, I'm going to focus mostly on the distributed systems. My focus is on system software. And system software, you can see, let me see if the pointer works. Yeah, system software lies here in the middle between application and hardware, and usually is built up of compiler, runtime libraries, operating system, and hypervisor. And there are some examples here on the sides. So usually in this area of research, we try to understand what functionalities, what structure, and also what algorithm you want to put in those blue blocks. And because the operating system is between software, application software, and hardware, we are always interested in trying to understand how we can change the operating system to make application faster, or how to adapt the operating system when there is new hardware. And this is what I'm going to talk about today. Obviously, I don't do my work just by myself, but I'm very lucky to have very good postdoc and PhD students. And obviously, I also work with undergraduate students. So most of our work is available online. Actually, all of our work is also open source. Okay, so let's now talk about research. So why I said in the first slide that we should sort of do research in system software for emerging heterogeneous platform. Like, why is that necessary? So first of all, as you know by the title of this workshop, we have applications that are very memory hungry, and those type of applications always existed. So everyone knows about database, ERP, CRM, or HPC, right? Those applications exist since decades. But today, what we have is data analytics and virtualization that are also memory hungry, but topic of this workshop, large language model. So those applications require a lot of memory. And they don't require just a lot of memory, but as we will discuss later, they are also compute hungry. So we want a lot of memory, but we also want a lot of compute. So what we can do? And in my presentation, after I will sort of look about the hardware changes in these last years, we are going to discuss what we should do, in my opinion, at the system software level. Okay, so this application requires a lot of compute. Therefore, the classic model of computers where we have a CPU in the middle, memory, disk, and network. This is what I studied when I was at the university. This is not good anymore because it cannot satisfy the application demands of the application that I showed you in the previous slide. So the hardware is changing. Every one of us knows about parallelism. We have many cores, many CPU in our computer, but also parallel memory, multiple type of memory. Oh, sorry, I said wrong. The same type of memory, but it's parallel, so we can access it in parallel and have additional bandwidth. Other than that, I think everyone today is aware of heterogeneous computing. So what does it mean is that in this picture, we are going to attach things like here, TPU, FPGA, or GPU. And I actually call this classical heterogeneity. And for me, classical heterogeneity is when I pair to a general processing unit like a x86, some special processing unit like a GPU or TPU. And classical heterogeneity is also CPU plus FPGA, which I call here reconfigurable hardware. And this can be plugged on the PCI bus in the same machine, but it can also be on the same socket. So we find, for example, CPUs from Intel that integrate FPGA and the CPU itself. As you can notice here, we just don't have the memory attached to the CPU, but we also have memory attached to these devices. Therefore, we start to see not just heterogeneous computing, but also heterogeneous memory, such as with different latency and can be either shared or private. So that's not the entire picture. What we're also seeing today is additional heterogeneity in the form of general purpose processor plus general purpose processor. So here, for example, we can attach some additional CPUs on the PCI bus or on the same socket. And while maybe this thing that is here that is called CYMI is not very famous anymore, people today knows about smart NICs or smart SSD. So storage devices or network devices that integrate, for example, ARM chips. There are many examples of this, and more recent, we also have computational devices on memory, such as UPMEM. So in this slide, just to make sure that everyone is on the same page, I put some examples. So everyone knows about Big Little, we have it in our phone. That's an example of this type of heterogeneity. Then there are several different embedded CPUs, such as ADShark or TI-OMAP, that have ARM plus DSP. And then very recently, there is this CPU, means SoC, Milk V Duo from, I think, China, that has both RISC-V and ARM sharing memory. What I showed you before is this, like CYMI or Smart NICs on the same machine, but also, as I mentioned before, we have some CPUs that are in memory. And there is UPMEM, Samsung, and some academic project like Emushik. Okay, so I think I convinced you that heterogeneity is a big thing, but at the beginning of my slide set, I said heterogeneous processing and heterogeneous memory. So what about heterogeneous memory? So we know that on the same socket, we may have multiple CPUs, and I showed you before, but what is interesting today is that on the same platform, we can connect memory not only directly to the CPU, but also through the PCI bus. And some examples of this are CXL or UB in Huawei. And there were obviously previous trials such as OpenCAPI, CCIX, and Gen Z. Okay, so how it does it look like if you put it in the previous picture? Well, so the connection between CPU and devices are now bigger because they are newer. PCI 5 is getting faster and with higher bandwidth. And now, because of this change, we are able to connect memory on the peripheral interconnect. That was not possible before. So we can have more memory to run our LLMs. And okay, so that's cool, but introduce further heterogeneity in the sense of latency. We can have persistent memory, volatile memory, and some of this memory may be cache coherent or non-cache coherent. So I represented this with these red lines. So as we can connect memory over here on the PCI bus, because the peripheral interconnect is by itself something that can, and that allows switches, we can also have further different levels of memory that goes through this orange block, the TSC switch. What will happen when we connect memory through this switch is that this memory will be obviously a little bit slower than the previous memory, but we can increase the capacity of our system and potentially also the bandwidth. Okay, before moving on and telling you about my work, I just want you to notice that potentially we could also connect another machine to the same switch. And not only 2, but 3, 4, and more. And in this case, we'll share the memory, this memory, through multiple machines. Okay, so say that, I will say that in the first part of my presentation, I will focus on this. And what you can understand by this picture is that the computers are not that simple anymore, but they are really complex. They may potentially have a lot of devices, a lot of different processing units that are heterogeneous, and also a lot of memory that is also heterogeneous. So it's not that simple anymore to program those machines. How do we want to program them? And also, in my opinion, non-trivial question, it's like, how can we fully exploit all these resources? And I'm saying about compute resources and memory resources. It's not trivial. It's a really difficult task for the programmer. Okay, so if we change a little bit the picture that I showed you before, and we put all the hardware down here in green, right? Let's reason a bit on how we can program this complex hardware today. So, by the way, I also put the shared memory potentially available with CXL. So, as you notice, our software, our entire software stack runs usually on the CPU, right? I mean, when we think about using a computer, we think of running the main software on the CPU. But we have a lot of different other processing units that can be general purpose, like on this side, or special purpose on this side. So to use those, we will need potentially some additional software on them, but our operating system on the CPU needs to have compiler support and also device drivers. When we go to our application, what we have to do in order to use all these potentially different processing units is to go and check in our application, for example, oh, this for loop maybe can run on the GPU. So we'll cut it out and use some programming framework to say, go run on the GPU. And then continue. For example, we find another piece of software that can run very well on the near data processing, so on the RAM. And then we cut it out and we use specific API to do that. So in general, we are going to end up from a code like this that is very simple. This is MPBAS serial, to a code that will add additional more calls, API statements, in order to take advantage of the heterogeneity in terms of processing unit. But wait, it's not just about that. It's also about the memory, because as you saw, we have a lot of different types of memories, and those memory may be private to some of those devices. Therefore, we have also to take care of the data movement. So it's very difficult to use these heterogeneous systems because it's not transparent to the programmer. We need to use a special API framework. So our code becomes increasingly more complex. So here I give you some old data actually. A serial code that has 454 lines may increase 177%. So we have to add additional code. Our programmer needs to know that, which is not always the case. And then many times we also have per address space pointers. So it's not just about the programming. As I said before, it's also about exploiting resources. How can I make sure that my work as a programmer will get maximum performance, or sometimes we care about energy efficiency or determinism. Especially many times as we learn heterogeneous programming, we don't think that we are using that potential machine by ourselves. But you know, in cloud, we are going to share resources, right? We are going to, for example, be running with another tenant that maybe will compete for the same GPU. But when we program, we always think like that we are the only one. So this, I think, is something that must change because especially cloud require people thinking that they are not the only one running them. Or we have to provide a transparent illusion that that actually happened. Okay, so I hope I convinced you that heterogeneous systems are complex and they are also complex to use. So can we avoid complexity? And how to avoid the complexity? So for me, maybe I'm a little bit old, I don't know, but I always thought that when I start learning programming, I learn programming on a single machine, and which I call here SMP, symmetric multiprocessor. And that, in my personal opinion, was simple. So could we program in the same way as we program on a single machine when we have an heterogeneous system? And as you hopefully remember from the previous slide, these platforms more or less look like SMP because they have shared memory amongst processing units. I'm also telling you they can do interrupt between these different cores, but they are not quite like SMP because they have heterogeneous ISA CPUs, heterogeneous cache, very diverse memory, uncoordinated boot, and etc. So my vision that I propose you today is that I actually want to research how to use and program those heterogeneous systems like SMP, like a single machine. Forgetting about complexity, I don't think it's possible to move, not that speaking. Yeah, sure it's possible. Okay, perfect. And therefore, now I lost the mouse, okay. And therefore, from a picture like this, in which the system software is only on the CPU, I want to move to something like this. So to provide an illusion of a single operating environment that I can use like SMP, because I find always the same interface, and also I can program like SMP. I don't want to care about heterogeneity. I don't want to think like this runs there, so I have to rewrite it, or this have to run there, I have to rewrite it. I want the system for me to take a decision by itself, based on a best decision that probably today we can find at runtime with AI, right? So we want to use the technology, we want to exploit it also to help the programmer to fully exploit those machines. So what I will show you today, what we have discussed today is about like this compiler here and this operating system here that enable this vision. But obviously that's only a part of the vision because more it's ongoing research or future work. So before delving into my work, I just want to kind of spend a couple of slides about the compiler part and the operating system part. So from a point of view of a compiler, I think what I really would like to see, part of my vision, is that a compiler that enable to compile those applications in a way that application can freely migrate between all these different heterogeneous processing units at runtime. So I don't want to have the programmer to take the program, analyze it, and then think this part goes there, this part goes there. I want to make it automatically. And I think that the only way to make it automatically, the decision is automatic and taken at the runtime, is to implement thread migration. So why? Why I want that? Because as I said, this is intuitive to program. I told you, I think SMP is simple. And thread migration also needs like a feature like one single address space, no data movement management, because it's done transparent for you. And no boilerplate code, because again, it's done transparent. So I also think that with thread migration, we could have efficient resource utilization, because based on some of the results, a few of them I will also show you later, that I had with my previous work, is that taking decision at runtime, especially when you share an hardware with other tenants, improve performance and utilization. And also, we can use resources that are currently unused. I don't know how many of you are involved or follow cloud. Fragmentation of resources is a big problem. And I think that with what I present you, that can be solved. The other part is the operating system. As I show you in my picture, my vision is that there should be like a single operating environment, right? And so why I want that? I want that because in my personal opinion, it's easy to program, but also to administer. So if you have multiple different machines or multiple different operating systems, you may need to create the same user in all of them, right? If you are the administrator. Instead, if you have a single operating system, you don't have to do that multiple times, but just once. Then we will have the same API and services and devices everywhere. And also, we don't have to think about the memory management because it's done automatically for you. So similarly to in the previous slide, also the single operating system may provide efficient resource utilization because a single operating system will have an holistic view of all the different tasks, but also of the utilization of every different processing unit. So with this holistic view, you can better decide, should I move a task on one side or on the other side? And at the same time, the operating system may also help with data migration decision. So the user doesn't have to do that. The application don't have to do that. I mean, because it's LLM, also a topic of today, maybe you can think about PyTorch, right? In PyTorch, you have to say to, for example, a matrix, to the current memory or to the memory of the GPU. In my view, that should be automated. Okay, so hopefully you are still all awake, and I convince you that heterogeneity is coming, and also heterogeneity is complex. So all these compiler and operating system that I would like to do, they look like. So what structure, and also how can we make them practical, right? So in the next slide, I will show you, and I will discuss a couple of, I mean, more than a couple, of my previous work that actually talk about how can we do thread migration across different type of heterogeneous processing unit. And specifically, I will first introduce you my work, the Popcorn Linux, that I started when I was a postdoc, and then improvement on this, first the Unifico and then each container. And all this project enables thread and process migration across two general purpose processors, and specifically ARM and x86. Then I will also tell you about the same work, but in the context of special purpose plus general purpose processor. So in the case of CPU plus GPU, or in the case of CPU plus FPGA. And we will talk about inter-mat kernel migration, inter-mat kernel migration also on FPGA, and then intra-mat kernel migration. So as you can see, my interest is not just about like ARM x86, but also about special purpose and general purpose migration. Okay, so in all of this, we don't have any shared memory between CPU FPGA or CPU GPU or ARM x86, okay? Because all this work started before CXL. Well, this is Popcorn Linux, the first, sorry, I have to move this one because, okay. So this is Popcorn Linux, one of my first work towards this vision. So the idea here is that I want to run application across x86 and ARM, and I want to move application transparently. So we introduced the idea of replicated kernel operating system, where there are two operating system kernel, one per CPU, but amongst it, there is this single system image that gives you the idea that you are always on one single machine, even if it is not true. Okay, so on top of it, because otherwise this will not work, we introduced a compiler framework that does some analysis and then is able to create one binary per ISA, so one binary for ARM and one binary for x86. And because of a slightly modified version of libc, we are able to migrate threads that are currently executing from ARM to x86 and the contrary at runtime. Okay, so let me give you a little bit more details. So first about the operating system, how this magic thing works, right? So we can have ARM and x86 that are connected via PCIe, TCP/IP, RDMA. We supported more or less whatever was available. And when we have two operating systems that want to do something together, we need to make them communicate. And we have this inter-kernel communication layer here. And on top of it, we developed, or we actually redeveloped some of the Linux subsystems so that they now can run distributed and called popcorn services here. On top of it, we were able to provide this single system image. So single system image means like the abstraction, the illusion that there is a single system running, a single operating system, by introducing this idea of popcorn namespace. I want to give you some more details further about the operating system. So specifically, if this is the Linux kernel in dark blue and it has this all different subsystem, what we did is to add some orange subsystem here to boot the operating system, the communication layer in green, and then the subsystem that we rewrote are this one in yellow. So network, file system, scheduling, migration, distributed IPC, and distributed shared memory. A little bit more details, and hopefully you appreciate it, about some of these subsystems. So the first one that I wanted to tell you is task migration. So with task migration, we are able to have a process, for example, that is running on x86, that at runtime migrates all its thread to ARM. So that's potentially not that difficult, and we shouldn't have done it maybe in operating system, someone can argue. But let's see instead this one, thread migration. So in the thread migration, if we have an application with 3 threads, the same as before, we want only to migrate, for example, 2 threads on x86 and keep running in this way. So this has to be implemented in the operating system itself and enable basically an application to span across different CPUs that obviously can be heterogeneous, but potentially they can also be homogeneous. So in order to do this, because when we started this project, there was no CXL, there was no shared memory across different cores, we had to implement DSM, so the illusion that there is a single memory across all this system ARM-x86. And what we did is that basically we took inspiration from cache coherency protocols and we implemented that at the page granularity. Okay, so for the sake of time, I want to switch to this single system image. So let's imagine that you have an application that runs on x86, no? And then we are going to migrate it on ARM. So when you migrate it from one side to the other side, and for example, you want to check what are the CPUs that are available in the system, you will see a different set of CPUs. Or if you migrate them on the other system, and you want to check, for example, what are the other applications, you will see another set of applications. So when we run our application, basically we run it in a namespace. And we want to keep the same namespace from one side to the other side. So what we had to do is to extend the Linux namespace that usually provide a sub-view of resources into this popcorn namespace that instead aggregates the resources that are available on x86 and also on ARM. So basically with this, that application that migrates will see exactly the same environment. And specifically what we did is that we are letting the application see, for example, all the CPUs available both on ARM and x86. And also we are letting the application to see all the memory available on ARM and x86. So if that application needs to communicate with other applications, we are going to let that application see also those other applications that, for example, exist only in x86. This is called namespaces, and we introduced it and presented it actually in one of the early versions of the Popcorn Linux. And specifically, we extended the users, file system, IPC, PID, network, CPU, and memory. Namespace are those, but we also enable IPC to work across these different machines. Because, for example, imagine that this application that was running initially in x86 is doing some few texts with another application running on x86. What are we going to do? Therefore, also IPC now are distributed. Okay, I told you about the compiler. So what we did with this compiler is to initially work on GCC, but then on LLVM. Our compiler has a profiler that we don't use much, but let's say that's there, that analyzes the application source code and decide which code should run where, or at least give some hints. And then we have our compiler toolchain that compiles the application so that the same application may run on a different ISA. So we do that by introducing a common address space layout, including TLS, but in this popcorn version without stack. And then we also add migration points. So migration points are those special points in which the application can actually migrate in a consistent way, I would say, between different architecture. And because we don't do we don't do some, let's say, stack transformation, we have to add this state transformation metadata, which actually increase the size of the binary. Our runtime framework supports this task migration and implements the state transformation when we go from one ISA to the other ISA. Okay, so I don't want to bother you further on this. This is like a work that is pretty well presented at conferences. We show that with this project, we can ease programmability because you take an application and magically you make it run on whatever x86 or ARM that you want. Therefore, we enable portability and legacy support of applications that have been written without, for example, the support for heterogeneity. We can also do improve resource utilization, and this we show it in the paper 1. When we have a heterogeneous ISA, overlapping heterogeneous ISA, and we can show up to 3.5 more performance when we do runtime scheduling decision versus static scheduling decision. And then on paper 2, that is related to this graph, where we show energy consumption here and the different set of processes here on the x-axis, we show that with fully heterogeneous ISA, ARM plus x86, we can do up to 66 better energy consumption. Okay, so how to interpret these numbers with heterogeneity? Obviously, if you have two different types of heterogeneous processors, one that is more energy hungry, such as x86, and one that is more energy efficient, just like ARM, this system that I present you allows you to dynamically take decision on where to run, for example, to improve energy efficiency. Okay, so hopefully you're still with me. We improve this work Popcorn Linux with this Unifico compiler. I wanted to mention this because this changed the way that we did the compiler toolchain, in the sense that now we are able to compile application with a unified address space, including everything. And it's very similar to what I showed before, so I'm not going to spend a lot of time. We still require some support from the operating system of the runtime when we migrate in order to remap registers. And the main advantage of this, that obviously we have a prototype and also we did a publication, is that before with the Popcorn that I showed before, so here is the size in megabyte in the y-axis, and here are different compilation of different programs. With Popcorn, the size of the, sorry, is this a spike? The Popcorn, the size of the binaries is very big, but with this compiler, we were able to reduce it and put it similar to normal static compilation. So this is not just a problem with the size, but it's also a problem from the point of view of security. And the interesting point is that what we did, that is basically strongly changed the way that compilers do compile application, the overhead is more or less invisible. So here is the speed up, so therefore under one is slow down. And here are different applications that we tried. And obviously this is a speed up versus the, let's say, normal compilation. And you can see that our speed down, if not FT that actually we fixed, is very limited. Okay, so how do we extend this work, for example, if we don't want to modify the operating system. Can we do that? So yeah, we did that with H containers. That is a modification of the popcorn that I showed you before, and in which we don't use to change the operating system, but we have a transpiration framework that is able to enable us to use CRIO. CRIO is a thing in Linux that allows you to migrate processes between different machines of the same ISA. But we extended it, so now we can do migration between ARM x86 and other ISA. We use the same compiler framework of Popcorn Linux, but we add a transpilation block that enables to take binary that are unmodified, so without the source code, and we can apply this popcorn idea to applications that we don't have the source code. So this has been done already, also published, support like even Docker, and it doesn't have any dependency on the operating system for companies that don't want to change the operating system code. It has minimal overhead, and it is presented in this graph. So if these are different applications that want to migrate, and this is the time that the migration take, our additional time is this yellow that, as you can see, you can barely see here. Okay, so far I told you mostly about heterogeneity in terms of general purpose plus general purpose. But what I wanted also to very quickly discuss today is about how can we take the same ideas that I showed before in the case of CPU and accelerator. So like CPU plus GPU or CPU plus FPGA. So we tried to do that, and the first attempt actually is more than 10 years ago. And we thought about inter-kernel CPU-GPU migration. So for example, in the cloud, sometimes a more high priority job arrive, and but your GPU is used. So what you do? So this is an attempt to solve that problem. We basically implemented something like this on the right, and what we did is to have an extended runtime for GPU that not only does decide at runtime if to use the GPU or the CPU, but is also to work together with the compiler that compiles your application, your mathematical kernel, to run not only on the GPU or TPU, but also on the CPU. So basically, when we have to compile something, we always compile for all the different type of accelerator or CPU that you have in your system. And then only at runtime, we decide, okay, we are going to use the GPU or we are going to use the CPU or the TPU. So some results here. So we basically show, but this was like more than 10 years ago. Now there are other works that basically work on top of this. But we run this on many different applications and also with many additional jobs in the system. And we show that by using dynamic decisions, we can get more and higher utilization of the system. Okay, so then because we were excited by this idea of inter-kernel migration of CPU plus GPU, we thought, can we do the same with CPU and FPGA? And so we introduced this XR track that actually does the exact same work that I showed before, but on CPU plus FPGA. And then because we continuously get this project rejected when we submitted to publication, we said, okay, let's make it even more complicated. And we do two different types of CPUs, so x86 and ARM, and FPGA. So this is very similar to the previous one. We have a compiler that compiles those mathematical kernel for x86, ARM, and also FPGA. And then at runtime, we have a framework that is able to decide where to place these different jobs. And again, we want to kind of improve utilization of the system. So some results again. So here, in this graph, we have the average execution time. So obviously, lower is better. And then we have different applications sets here on the x-axis. So the different colors show vanilla Linux, x86, vanilla Linux ARM, and FPGA. And then the possibility to run instead in blue with our framework that is called XRTrack. So as you can see here, we are more or less always the fastest. And when we look at instead at the throughput in the second graph, you can see that also for the blue one, that is our solution, we can achieve higher throughput. So again, this work shows that with runtime decision making, we can reduce the average execution time, maximize the throughput, and enabling utilization of potentially idle resources in the cloud. But obviously, as every research work in academia, it has some limitation. For example, we only support C language. Okay, the most recent work in this line of work is this. I call it Dale, but to be honest, it's under submission, so it's not the real name. So we try to ask ourselves, okay, so now we are able to do thread migration in x86, and we can also do intra-mathematical kernel migration. Sorry, Intel. Can we try to do intra-kernel CPU FPGA migration? So what does it mean intra-kernel? So the majority of usage in AI of GPU is that we send a lot of small kernel to the GPU, but actually we find out that there are some applications like in bio that they have really large kernels. So we thought, okay, so let's say that the FPGA has a fault and then it interrupts midway. Can we restore that execution on the CPU? And we did it. So in order to do that, the main idea is that we automatically insert checkpoints into the mathematical kernel so that if a fault happens, we can restart the execution of it in the CPU. And in this way, we basically were able to introduce also inter-mathematical kernel CPU to FPGA migration. So we showed this is possible in this paper that is under submission. It obviously, unfortunately, has some overhead, and if you want, this is the normalized overhead. In certain cases, it's really brutal, but by the way, this is not the last graph, but we can do it. And while the overhead in terms of time can be high, the overhead in terms of additional circuit that we have to put in our FPGA is actually quite low. So this is for different mathematical kernels. And as you can see, 9, 0.7, 1.8%. Okay, so this is everything that I wanted to tell you about heterogeneous process migration. I'm sorry, hopefully I'm not too late. I also want to talk a very little bit about heterogeneous memory. Do I have enough time? Can you give me another 5 minutes? Okay. Yes. Okay, so I also want to talk about memory. So why I want to talk about memory, I think I already justified before, because today we have, for example, CXL that allow us to connect multiple machines to enable the shared of memory. And okay, CXL is not the only platform that enable that. I showed you also before that, for example, we can connect multiple machines through AMBA key in an embedded system, but then there are other solutions like coming from academia, like OpenPython. But okay, let's focus on CXL 3.0. We can do something like this. We can connect multiple machines to a CXL switch that then connects to memory. What we want to do with that? We want to, at least in my opinion, have a single operating environment amongst all of these machines that enable all the memory and all the CPUs to be shared. So why I want to do that? I want to do that obviously because I have LLMs. Memory is a big problem, but also you want a lot of compute. So if you are able to provide a single operating environment in this scenario, you will be able to basically use all the CPUs that you have available here. That can be, okay, in this case, they are only CPU, but potentially you can connect also GPU. and also all the memory that is connected on these nodes and also on the CXL switch. So what to do? So we thought about it, and we thought, okay, can I run an SMP operating system per machine? Obviously, I can do that, but then I need to make my application communicate, and that's not easy. So can I use a multi-kernel? That is what I showed you before about Popcorn Linux. And then the answer is like, yeah, actually, I can use a multi-kernel, assuming that I can make a Popcorn Linux commercially grade. But the problem is that with multiple kernels, we don't exploit shared memory. And there are communication overhead. So we come up with this new design that is fused kernel, where we solve the problem of of communication overhead by reducing it, and also we let kernels exploit shared memory. And this is called Stramash Linux. Okay, so maybe I don't have the time to go very quick through this, but so the state of the art, these multiple kernel operating systems such as Barrelfish and Popcorn that I showed you before, it has overhead because they come with the idea they don't share the memory, and therefore they spend a lot of time in message passing. Instead, in our design, we do shared memory when we can, and therefore we reduce the overhead on the message passing. Okay, so excuse me, I would like to kind of present it a little bit more, but I understand that maybe I should finish as soon as possible. We call this new design Fused OS, and we say that it falls behind the idea of shared mostly. And as I said already, the design principle is that when we have to communicate between kernel, we want to avoid message passing and prefer instead hardware implemented coherent shared memory. So it looks like this, so very similar to the Popcorn Linux that I showed before, but it used the shared memory. In the case of heterogeneity, we keep using the runtime and compiler framework from Popcorn that I showed you before. Therefore, we don't have to spend more time to present it. And we can instead discuss very quickly a few internals of the operating system. So we still have an interkernel communication layer when we cannot use the shared data structure here on the shared memory. And on top of it, we develop the distributed operating system with message passing, taking them from Popcorn. But also some of those global operating system services are now running not anymore on communication layer, but on the shared data structure provided by Stramash. And obviously, we also have here a single system image. So we focused on memory management, and we implemented several components that are working for both heterogeneous ISA and homogeneous ISA platform. These are single kernel level virtual address space. We have a global interkernel memory allocator, and we also have a global interkernel page cache, interrupt rerouting, and boot up sequences. To support heterogeneity, we introduced the idea of remote walkers and data converter, and those are used for the page table, VMA, page faults, and etc. Because we don't have a CXL switch, we cannot really create what I showed you before. And instead of that, my student implemented a QEMU environment that also has some functionality similar to Gen 5 in order to have a little bit of cycle accuracy in our evaluation. And that has been done by extending the QEMU L1 cache simulator to L1, L2, L3, and also CXL. Okay, so I have to say that likely this work has been accepted at ASPLOS and will be presented by Tong that is here in a few weeks. And we show that basically with exploiting the cache coherency of CXL, we can improve the performance of the Popcorn Linux. And here there are some results, but let me just jump to conclusion so that I'm only less than 5 minutes late. So, okay, so what I wanted to communicate with this talk is that, so we have a lot of heterogeneity in the hardware that is coming up, heterogeneity in CPU and also in memory. And I think that the software is lagging behind. And in order to better use this hardware, we require new design, new system software design. So for better programmability, exploitability, and also energy efficiency and fault tolerance. And I told you my vision of this single operating system, single environment that goes across all these different heterogeneous processing units. I also show you that in order to implement that, we need thread migration, and some of my work already implemented it, but more work is needed. So we need the new OS design and abstraction, including multiple kernel and fused kernel, but also a compiler to support this heterogeneous ISA and heterogeneous memory. Okay, thank you, and sorry I was a little bit maybe too long.
Okay, thank you, Antonio, for that insightful presentation on operating system, heterogeneous for heterogeneous processing. Especially for your extra gift. Thank you so much.
Thank you.
Yeah, it's time for question. Yeah, any question? Sorry.
Thanks for the presentation, very interesting talk. So one quick question. So especially for single system in Bayes, and if you look at from a scalability perspective, like maybe rack scale system. So how do you see it? Because if you have a large scale systems, like you have different topology, network topologies, so how it will impact from performance perspective?
Yeah. So okay, this is a very good question. So okay, so actually, the majority of the work that I show you today has been done on a single machine, right? But obviously, when you go outside of the machine, especially with CXL on with the shared memory, now you're going to think, okay, so there will be multiple nodes connected to the same memory. Will the cache coherency, hardware cache coherency scale? So probably no, it wouldn't scale. And in fact, what we actually submitted to AutoS, to the AutoS, ICYMI AutoS, is that an analysis of that, which part of it is also in the last work that I show you, the Stramash, which try to kind of say, okay, because the cache coherency of the CXL probably will not scale, can we do an hybrid of DSM, so software consistency, and cache coherency in hardware? So we are looking at doing an hybrid to scale on CXL, and there will be also different type of algorithm, because obviously you don't need always strong consistency. So you may have like strong consistency, relaxed consistency. This will be enforced by hardware cache coherency, or maybe enforced by software consistency, and then it could be an ownership protocol, and etc. So it will be just an hybrid of all of this, we think at least, because otherwise scalability will be the main bottleneck of those systems. And probably at that point, the people that are doing, instead of CXL, they are doing the unified Ethernet, or I don't remember, I think Ultra Ethernet, probably they will have the best chance to succeed instead of the people that do CXL.
So I guess the programming model needs to be changed as well?
No, yeah, so I mean, I think we can do a mix. We can do, so I don't think the programming model have to be changed necessary. I think that we can provide the different consistency levels, and potentially, yeah, sure, we can also change the programming model, but I don't think it's necessary, fully necessary. But at least that's my view.
Okay, thank you. Any other questions? For online friends, you can put your questions in the chat box. Okay.
Thanks, Antonio, for a very nice talk. Was wondering if you've considered, for example, applying these techniques on a hypervisor level. So, for example, if we consider the hypervisor in a distributed environment, you could potentially run instances of that hypervisor on different nodes and delegate kind of the operations needed to do memory sharing, address translations to the emulation layer of that hypervisor. So have you actually considered that approach, and If you did, what do you think the differences are between Popcorn Linux and that approach, and what are the cons of that? Just curious. Thanks.
Okay, yeah, thank you for the question. So yes, I already presented too many things. So we actually have we had a project and a paper about moving the same ideas that I presented here at the hypervisor, the flag visor that we presented in EuroSys 2023. And so we basically have a distributed hypervisor, but it only supports homogeneous system. So it's only for example, OX86 or all ARM. Okay, I say we, but actually the student was working at Virginia Tech. Also tried to look at the problem of doing whatever I show you here, so heterogeneity with hypervisor, but we weren't able to make anything run on it if not as a very small operating system for embedded systems. Like, I think it was Fuchsia. We tried to run Fuchsia on it, but I mean, we weren't able to also get numbers because we don't have the hardware with the shared memory, right? So I think, yes, you are right, but even if, let's say, we have CXL later where we share the memory, we will not be able to run an hypervisor transparently on it, but we will need to kind of create an hypervisor that may run across the CXL with some of the techniques that I presented here and also that there are in that paper, FragVisor. So yeah, in synthesis, I would say that, yeah, we also tried to kind of look at these techniques from an hypervisor point of view. Certain things are easy to do. Like if you look at the homogeneity, several ideas can be brought from here to there. But then when you look at heterogeneity with hypervisor, it's a bit more complicated because what software are you running there? Because you have to change drastically the entire system software that runs on it. So here we just recompile the application. But if you do an heterogeneous hypervisor, then you also have to recompile the operating system. And it's kind of, I mean, we thought it's kind of impossible to take Linux as it is and let it run on something like that, while obviously we can run Popcorn, but we will not be able to kind of exploit the same idea and reuse them there. This is why we choose the layer of operating system where we look at heterogeneity. Hopefully I answered your question.
Okay, thank you, Antonio. Any further questions? Okay, thank you again, Antonio. Thanks very much. Okay.